In this video, we're continuing with Chapter 3, Differentiation Rules. We're going to go through Section 3.6, Derivatives of Logarithmic Functions. Okay, so similar to how the formulas for the derivatives of inverse trig functions were found with implicit differentiation, the derivative of the general logarithm, so log base b of x, is found using implicit differentiation. So if you let y is equal to log base b of x, right? So we're trying to find the derivative of, we're trying to find dy dx, where y is equal to log base b of x. But you can write this as b to the y power is equal to x, and then do implicit differentiation, because we know the formula for the derivative of exponentials. And this is what you get. Now, if you have a natural log, then it's base e, right? Natural log of x means log base e of x. Natural log of e is 1, so the derivative of the natural log of x is just 1 over x. But again, in general, for logs, this is the formula for the derivative. Okay, now they give formulas for the chain rule, but just as long as you understand the chain rule, you shouldn't need these formulas. We'll work examples doing chain rule with logarithmic functions in the next video. Okay, here, more examples. We're going to work a bunch of examples. Okay, so here they're finding f prime x of the natural log of the absolute value of x. So f of x, you can write this as natural log of x if x is greater than 0, or natural log of minus x if x is less than 0, right? Right. That's how you define that. That's how an absolute value is written, because if x is greater than 0, then just put x. X can't be equal to 0 when it comes to a logarithm. But if x is, if x is less than 0, then just put a minus sign out front, because then you're going to get minus, and so that's what this is, right? Think about the definition of the absolute value. We go over that in algebra. And so you can take the derivative of each one of these separately, and you get, we just showed this formula on the previous page, that the derivative of natural log of x is 1 over x. You get 1 over x here, and then just use the chain rule. So 1 over minus x times minus 1, you get 1 over x in general. So the derivative with respect to x of the natural log of the absolute value of x is 1 over x. Okay, logarithmic differentiation. The calculation of derivatives of complicated functions involving products, quotients, or powers can often be simplified by taking logarithms. The method used in the following example is called logarithmic differentiation. So you can use logarithmic differentiation if maybe it's the only way you can find the derivative, or maybe it just makes the derivative a lot simpler. So they give an example here. You could find this derivative using methods we already have learned. So the quotient rule here, and then you'd have to use the product rule for this top derivative, and in combination with the chain rule. And so it seems pretty complicated, but if you take the logarithm of both sides and they do the natural log, and you can imagine in calculus, you want to use the natural log if you're going to use logarithms as much as possible, because the natural log are like e to the x, anything with e, because e is simple in calculus, right? Natural log of x is just 1 over x. That's the derivative. The derivative of e to the x is just e to the x. So natural logs and exponentials with e are your friend in calculus. So you take the log of both sides, and you can use any log, but you might as well use the natural log. And the natural log of all of this, the logarithm of all of this, you can simplify that, right? You can separate these into the natural log of this minus this, and then you can separate it into the natural log of this plus this minus this, right? Then you can bring this 5 out front. They bring the 1/2 down. They bring the 3/4 out front. They bring the 1/2 out front, this 1/2 power on the square root. They bring the 3/4 out front. And then they do implicit differentiation to find dy dx. Okay, so they solve for dy dx. They get this. Now they've got y here, so they substitute y back in. And there's dy dx, right? That's a hell of a lot simpler and easier to do than using the quotient rule there. So we're going to do a bunch of examples of logarithmic differentiation. The steps are that, again, you take the natural logarithm of both sides of an equation, y is equal to f of x. and then use the laws of logarithms to simplify. That's the idea. It's going to be easy to simplify. Then differentiate implicitly with respect to x and solve the resulting equation for y prime. And if you've got, when you solve for y prime, if you've got y by like y explicitly defined on the opposite side of y prime, then substitute for f of x back in for that y. Now it says that, so if f of x is less than 0 for some values of x, then the natural log of f of x is not defined, right? So if we come back here, what about when this y, for values of x where where y is less than 0? This is undefined, isn't it? Natural log of y. Well, you don't have to worry about that because, so if you start off by just saying, okay, the absolute value of y is equal to the absolute value of fx, right? And then you go from there and you find dy dx. So you start off with this and you find dy dx. You're going to get the exact same result as if you just didn't put the absolute values and just did it kind of assuming that it's always positive anyway. And they do this. So if we look here, they're going to prove the power rule. So y is equal to x to the n. They take the natural log of both sides, but they use that absolute value, right? And because of that property that the derivative of the natural log of the absolute value of x, or of anything, is 1 over x, well, you know, you get rid of the absolute value, that's what happens. You just get this here, and it proves the general form of the power rule. So with logarithmic differentiation, you don't have to worry about when f of x is negative. Okay. The number e as a limit. We have shown that if f of x is equal to natural log of x, then f prime is 1 over x. Thus, f prime of 1 is equal to 1, right? F prime of 1 is equal to 1. We now use this fact to express the number e as a limit. So they want to write the definition of e as a limit. We've talked about e once so far in this textbook. So that was in section 3.1. We were finding the general equation for the derivative of exponential functions using the definition of the derivative. So we started with f of x is equal to b to the x power. And so we said f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. We plugged in b to the x, simplified, and this is the result. The limit as h goes to 0 of b to the x power times b to the h minus 1 over h. But b to the x is not a function of h, so you could bring that out front. And so f prime of x for an exponential function is this b to the x times this limit here, as h, the limit as h goes to 0 of b to the h minus 1 over h. And so what we saw is if we come here, this b to the h minus 1 over h, that's f prime of 0. Because if we come back here, if we want to find f prime at 0, that's b to the 0 plus h, that's b to the h minus b to the 0, which is 1 over h, right? That's what this is. So f prime of x is equal to this f prime of 0 b times b to the x. Now, there's a number. We saw that there's a number for b, right? The base, where we're evaluating the derivative of b to the x. So when the base is a certain number, this f prime of 0 is equal to 1, which is interesting because that means that f prime of x is just b to the x. And that number, if we come here, that number is e. That's this limit here. That number is e. The derivative of e to the x is just e to the x. Now, this is not a definition of e, right? We're not saying e is equal to something. It's just kind of a way of looking at what e is. This is just this limit is equal to 1. Here, they want to give a definition of e, like what is e equal to as a limit. And so what they do is they take the derivative of this using the definition of the derivative. So this f prime of x, but we're going to evaluate it at 1. So the limit as h approaches 0 of, and how do you do this? You say x plus h, but x is 1 in this case, minus f of 1 over h. Then they substitute x for h. They substitute in the function, so natural log of x. Simplify to this point, bring this as a power, and you get this. Limit as x approaches 0 of natural log of 1 plus x to the 1 over x power. But because f prime of 1 is equal to 1, this limit is equal to 1, right? Now, what they do is they say, okay, by theorem 2.5.8 in the continuity of the exponential function, we have, so e is equal to e to the first power. So e, this is 1, but what is 1 equal to? They put this limit in here. But now they can bring this limit, they can bring e inside of that limit, and they use that theorem 2.5.8. And if we come to that theorem, that's just saying how, okay, if f is continuous at b, so this is like saying if e to the whatever power is continuous at b, and the limit as x approaches a of g of x is equal to b, like 1, right? So this is that limit that's equal to 1. Well, we know that e to the 1 power is continuous at 1. Then you can just say, you can bring the limit out front of the function. Or you can bring the function inside of the limit. And that's what they do here. Now you've got e to the natural log, so that removes the e in the natural log, and you're just left with this. So this limit is equal to e. So that's one way you can derive what e is equal to. But you can get an even simpler look at this. They substitute n is equal to 1 over x into this formula, and they get another form of e. Here, the limit as n approaches infinity, right? Remember how you do substitutions with limits of 1 plus 1 over n to the n power. So this is just two different forms. This is as x approaches 0. This is as n approaches infinity. Okay, that's it for this section. Next, we're going to work some example problems.